Welcome to qnawire.
All right. So I think this will be good to have some examples for. So imagine that we've got the following molecule, right? This is a stereo. This has stereochemistry. Imagine that we have the enantiomer of this. Then imagine that we have diastereomers of it, in which we only change one of the two stereocenters, one where we change the bromine to a dash and one where we change the OH to a dash, each time leaving the other stereocenter unchanged. Okay, now that we've got this, I think this might help us answer some of the questions. So these are indeed all stereoisomers of each other. You'll notice these are enantiomers of each other, whereas these are diastereomers. Maybe I'll use a different color. So we've got diastereomers connected in blue and enantiomers connected in black. Okay, stereoisomers always have the same molecular formula. Yeah, that's, basically the point, right? So A is true. If they didn't have the same molecular formula, they wouldn't be stereoisomers. They'd just be different molecules altogether. Okay. B, stereoisomers always have the same structural formula. And this is false, right? So a structural formula includes all three-dimensional information about the molecule. So the fact that this is a wedge as opposed to a dash, that's part of the structural formula, right? Yeah. So structural formulas include stereochemical information. C, stereoisomers are always non-superimposable mirror images of each other. And this is where it helps. As I said, the blue lines connect diastereomers, and diastereomers are indeed stereoisomers, right? They're molecules that differ only in their stereochemistry, and you can clearly see that these are not mirror images, right? The mirror images are the enantiomers, but we can still have stereoisomers that are not enantiomers, so long as we have more than one stereocenter. So C is false. And D, stereoisomers always possess handedness. And here the answer is no. And we can give an example. Really, we can just use the same example, but instead of bromine, right? Let's take a look at this. Whoa. Okay, here's an example where these are all stereoisomers of each other, right? So these are still diastereomers. In fact, the blue lines connect all the diastereomers. And in fact, this black line here is going to connect enantiomers. But what you'll find is that due to the symmetry of this molecule and this molecule, that they are not actually enantiomers. They are, in fact, the same molecule, right? So these are stereoisomers of each other, and they don't have handedness, right? They're identical to their own mirror image. These are what are known as meso compounds. These are meso compounds, and specifically they're meso stereoisomers. That is to say, they have a line of mirror symmetry that goes through them. For example, you could consider this to be a line of mirror symmetry that goes through them, right? They have two or more stereocenters in the line of mirror symmetry, in which you can envision swapping out the stereocenters RR to SS, but in fact, in doing so, you would just get the same exact molecule back. For example, we can simply rotate this molecule to some extent. Give it like 180 degrees in that direction, and then flip the forward to the front 180 degrees, and you would be back to the wedge version, right? So these are stereocenters, but they're actually they're stereoisomers, but they're achiral. And if they're achiral, they don't have left or right handedness. So D is false.